those are called A and B also. A and B are called the independent events because you can see that even if the event B is occurred, it does not, affect the probability of A. And that is why those events are called the independent events. Because occurrence of one event does not affect the occurrence of the other event. Similarly, if I have a probability of B when A is occurred, in that case too, what will happen is we'll get probability of B. Fine. Example. A random experiment, uh, random experiment results in an integer outcome between 1 to 10. Results in an integer outcome between 1 and 10, both inclusive. All numbers are equally likely. All numbers are equally likely. Let capital A and capital B be events that an odd number occurs. Okay, I'll write it in this way. Capital A be event that an odd number occurs. And B be the event that a number is divisible by 3 occurs. The event that the number divisible by 3 occurs. Obtain probability of A condition B. Second, probability of B condition A. 3, probability of A complement given B. Fourth, probability of A condition B complement. And fifth, probability of A complement condition B complement. Let's write down the events here. First of all, the sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The event A is that you get an odd number. You'll get odd number is 1,
1, 3,
3,
5, 7, 9.
7, 9. The event B is
3, 6, 9.
3, 6, and 9. Look, first three of them we can easily find out. Probability of A condition B condition A, probability of A complement condition B also it is possible. But in this case, what you have probability of A condition B complement. Okay. So for that, what we will need is we'll need B complement, and in the last one we'll need both A complement and B complement. So why I'm saying this is we have seen that probability of A complement condition B. The formula for this was 1 minus probability of A condition B. This we have seen yesterday. But we don't know what happens when there is A condition B complement. And for this reason, what I will do is I'll go by the straightforward formulas where you have probability of intersection divided by the other one. So what we will do here is I'll write down A complement. A complement is 2, 4, 6, 8, 10. And B complement is 1, 2, 4, 5, 7, 8, and 10. So let's find out the probabilities. So probability of A condition B. This is equal to probability of A intersection B upon probability of B. What is A intersection B? How many elements do we have in that? So 3,
3 and 9.
9.
3 and 9.
So we'll have 2 by 10 upon probability of B 3 by 10. This is 2 by 3. The first one. Probability of B given A. Yes, anyone?
2 by 5.
2 by 5. Third.
So 2 by 3 again.
It is
2 by 3.
sure.
So 1 by 3.
1 by 3.
1 by 3.
There are no 2 points in the intersection. A complement and B. If you take the intersection, there is just 1 point there. Fourth one. Probability of A condition B complement is equal to
3 by 7.
3/7. The last one.
4/7.
Is 4/7. Probability of A complement condition B complement. This is 4/7. Next example. A card is drawn. A card is drawn. Saurav, will you please mute yourself? Is drawn from an ordinary pack. From an ordinary pack of 52 cards. What is the probability? What is probability that it is king? That it is king. Given that it is a face card. How many face cards do you have? What do you mean by face card, first of all?
12 face cards.
There are 12 face cards. By face card, I mean that the drawn card is a jack, queen, or a king. Okay, so three of each color. So there are 12 face cards. And how many kings do we have? We have 4 kings.
Four.
So let's just define the events first of all. Always look here and in the further topics also, whichever we will learn. Always try to define the event. It will enhance your understanding of the problem. Even if you feel that you can do it orally, think of the event. What is the event? So A is the event that the drawn card is king. Card is king. The event B is card is a face card. So we need to find the probability of A when B is occurred. So that is equal to probability of A intersection B upon probability of B. So number of elements in A intersection B upon number of elements in your sample space upon number of elements in B upon number of elements in sample space. Just to cancel out, and what we have is number of elements in A intersection B upon number of elements in B. So how many elements do we have in the intersection?
4.
4. and number of
12.
elements is
12.
1 by fine. Next one. Personnel department of a company has 100 engineers. Has 100 engineers whose whose distribution is as below. So age in years, BE, ME, and total 20 to 30, 30 to 40, greater than or equal to 40. The 20, 25, 10, 5, 10, 30, 25, to 55. If one engineer is selected at random, if one engineer selected at random, first one, find probability that he is only B, probability that he is only BE. Second, his master's degree given that his age is beyond 40. He is ME given that age above 40. And the third one, he is under 30, under 30, given that he has ME degree. Yes. So let's define the event first of all. Yes, tell me what could be the first event A. Look at the things that you need to find out, and according to that, you define the events.
Sir, event A will be he will have only BE degree.
An engineer is only BE. An engineer is only BE. B. Look at the second one. He's master's degree. So event B I will define as an engineer has master's degree. Engineer has ME. What about the event C? What is the condition? Given that age is above 40, so I will make an event that engineer is above 40. Engineers age above 40. So if you combine this B and C, you can find out the probability for second one. What about D?
An engineer under 30.
An engineer under 30. Yes. Tell me the first probability.
55 upon 100.
55 upon 100 exactly. So I'll write down the answers here. You can. So first is that simply the engineer needs to be below 30. Okay, so we'll look at the total number of engineers between 20 and 30 is 25. So probability of A is equal to, oh sorry. Engineers under the first probability that he is only B. Sorry. Yes, he is only B. The total number is 55. So 55 divided by total number of engineers. What's the next one? He is ME given that age above 40. So probability of B when A is occurred, I mean above 40. So C.
Sir, that is C. For B, it will be of 45 upon 100 that we missed.
The first question is probability that he is only B.
Yeah, that is done. Then,
Huh.
okay,
Second
okay.
is,
Yes, I just got. Okay.
yes, what about this? Probability of B intersection C upon probability of C. B is that he is an ME and C is that above 40. How many engineers are having ME as well as those are above 40? That will be probability of A intersection B, right? In B intersection C. So they need to be above 40 as well as they should hold the ME degree. What is the answer?
30 by 45.
30 by 45.
30 by probability of number of elements in C. How many elements? There are 30. Why you're saying 35?
So 30 by 45.
45.
Why 45?
But it's not the final probability. It's P of B intersection C, 30 by 45. And then whole upon 45,
No, no, no,
45.
no. No,
So it
no.
will be 30 upon 40.
30 upon 40. That is the correct answer because look what you are looking at. The numerator is B intersection C. That he is an ME as well as he is above 40. So how many are there? There are this 30. Those are the age is above 40 and they are holding the ME degree. So numerator is 30 upon the total is 100. So I will cancel it out with the denominator. So number of elements in C. What is C? Engineers above the age of 40. What is the total number of engineers above age of 40 is this number. This is 40. Am I clear? So the answer
Yes,
is
sir.
35. Next, probability of under 30 given that he is MA. Probability of D condition B. What is it?
Pi by 25.
No.
5 by 45.
5 by 45.
So that is
1 by 9.
1 by 9.
that is final answer. Okay. This another theorem. Let A and B be any two events defined on sigma. Then probability of A intersection B is equal to probability of A condition B into probability of B, which is also equal to probability of B condition A into probability of A. This is called the multiplication theorem. Hard to prove? Can you prove it? It's called the multiplication theorem. Can you prove it?
So we'll use conditional probability and just
No,
make
just
the
adjust the terms
definition.
according to your requirement. Fine.
Yes.
Now we are heading towards the Bayes theorem, which is a very important part. Uh, but first of all, we'll see what is partition of samples. We have seen the partition, I guess. What is partition? In your discrete mathematics course, you may have seen partition. What is partition? Partition of a set. Have you heard the term at least?
Heard of.
Sir, partition means I think it is grouping of elements.
Okay. Have you heard this, Saurav, in discrete mathematics partition?
About partition of sample space, that I don't know, but sample space we have.
Sample space. Nice one. Okay. Have you heard of equivalence classes?
In discrete mathematics, you're asking?
Yes.
Not equivalence classes. He
Equivalence.
he taught us a relation, equivalence relation.
Just tell me, Shivani.
So it should equivalence relation, right?
Yes.
It should be transitive, reflexive, and one more thing.
Symmetric.
Symmetric.
Yeah.
So what happens when these three properties are there?
Then it is equivalence relation.
So using equivalence relation, you derive the equivalence class.
Okay.
Okay, so if we are not very much clear with that, what I will directly do is I'll define this and I'll explain you what happens in this. So what do we mean by partition? Partition is simply that you divide the entire structure into mutually exclusive parts. So it is simply like if you have a sample space S, what I'm going to do is I'll divide this complete structure into mutually exclusive and exhaustive events. What words did I use? Mutually exclusive, mutually exclusive, and exhaustive events. What is mutually exclusive? So they don't have anything in common, first condition. And the next condition is exhaustive. Which events are called exhaustive events? Which events are exhaustive events?
Sir, their union is the sample space.
The union is the sample space. So
Means up
what do we
to
call
A and it is sigma, yes.
the collection of mutually exclusive and exhaustive events? Is called partition of a sample space. Is called partition partition of sample space. I'll just write this down and say mathematical form if A1, A2 up to AN are events. Events defined on sigma. I'll call this capital M. Then this M is partition if the first condition, second condition. Tell me. If
So
you
actually,
take
it's
if AI intersection AJ is equal to phi for all I comma j. If you take any two events and you take the intersection, it is always going to be empty. The other condition, union I is running from 1 to n, will become the complete set sigma.
Sir, what is the first condition? AI.
Intersection AJ. Okay, I'll quickly just mention. Okay, no problem. Tomorrow I will introduce the base theorem, we'll solve the example and we'll end this. So once we are done with tomorrow's lecture, we'll be done with basic probability and we'll be completely ready to introduce the probability distributions or continuous probability distribution, then discrete probability distributions, and we will look at binomial, normal, and all the different type of distributions that we have.